Hello everybody, I'm your host Hal Curtis and I'd like to welcome you to The Space Industry by satsearch, where we share stories about the companies taking us into orbit. In this podcast, we delve into the opinions and expertise of the people behind the commercial space organisations of today who could become the household names of tomorrow. Before we get started with the episode, remember you can find out more information about the suppliers, products and innovations that are mentioned in this discussion on the global marketplace for space at satsearch.com. Hello everybody and welcome to the episode. I'm joined today by Maciej, a machine learning software engineer at satsearch member company KP Labs. KP Labs is based in Poland and develops solutions that bring greater autonomy to space. Today we're going to be discussing the algorithms and hardware that can enable the running of machine learning in space missions. Hi, Maciej, welcome to the episode. Great to have you here. Is there anything you'd like to add to that introduction?
Hi, welcome. Pleased to be here. Not really, we can get to the topic.
Okay, fantastic. So this is a really interesting topic, one that's getting a lot of attention in the industry as the amount of data and capabilities that satellites have increases. And obviously there are limitations on communication between satellites, communication in particular with the ground, that these sorts of solutions are trying to overcome, problems they're trying to address, as well as enable new capabilities, new business models, new research opportunities. So onboard data processing, or OBDP, and the use of AI are becoming increasingly important in the industry, like I just mentioned. What do you think is driving this?
So first we need to really understand and highlight the difference between the traditional approach, how stuff used to be done in the past, versus the new approach with the onboard data processing. So throughout this talk, I've been mainly focusing on Earth observation satellites that process images, that capture images of Earth and process them. And in this context, in the traditional scheme of things, satellites perform little to no independent tasks, and they are treated as data gathering devices that send bursts of images to ground stations via radio connection. And this connection that enables sending data from satellite to ground station is called downlink. And after satellite captures photos, sends them down to Earth, it is processed inside a data center. And this is how things used to be done. And the new approach is quite opposite: to gather data and process it on board of satellite, make satellite be aware of the data that it captures. And in this new approach, we transmit only results of data that has been processed. We send valuable results, and we don't have to process everything. We don't have to transmit everything and then process it inside a data center. So I believe that there are two factors driving this shift in paradigm: limitations of the old approach and emerging possibilities with the new one. So let's get started with what was wrong, what was problematic with the old way of processing data. So the main limitations was transmission, was the communication, because in most scenarios you can communicate with your satellite when it flies over your ground station. And if you want to have more connection, you have to build more ground station. It is very expensive. And your satellite is still very dependent on those ground stations. This creates a lot of problems because the communication is scarce. It is really expensive to build new ground stations. Communication can take long. There is latency in the whole process. There may come some communication gaps, mainly when satellite flies over different part of world when you don't have ground stations. And to really provide you with an insight of how big this problem is and how different new way of processing data will be, in the old way, 15 to 20% of what satellites transfer is useful. Like 80% of photos that we send via this downlink connection in old ways of doing things is invaluable. So the communication is really expensive, and we waste it on sending data that may be cloudy or blurred. So there is a lot to improve. Now, what is driving this shift also, as I said, is the possibility of something new with new technologies, novel ideas, new space missions. And I want to maybe get a bit off track and say about this shift of thinking about satellites in wider context, because it is very important connected with onboard data processing. Because there has been a shift towards more agile and more rapid development of satellites that are more focused on AI experiments, new technologies. And this is the wider reason for this movement towards AI. And for example, at KP Labs, we work on something called Smart Mission Ecosystem that grants great flexibility and ease of use. And previously, you could either buy a pre-made, hard to customize satellite or create your own solution from scratch, but you had to do the heavy lifting by building your custom design. So in this new paradigm with this new approach, we really want to hit the sweet spot between building stuff from scratch and buying something that is hard to customize. And we provide Smart Mission Ecosystem, which comes with many building blocks for creating your solution with our hardware, our AI accelerator, software for satellites, machine learning algorithms, and they are provided as building blocks. And they are not only easy to build on top of, but they also come with many great convenient tools, environments for testing. And all of that creates a new wave of satellites and new approach with emerging popularity of CubeSat standard, smaller satellites. And what I have described, this new approach with building blocks that enable onboard data processing, on the lowest level, it stems from advancement, gradual change in more available technology, microprocessors, tooling, and things that are not necessarily connected to satellites, but companies like KP Labs can create building blocks out of those basic components, and then the end user can create smart missions out of those building blocks. So there is a ladder of cooperation, new technologies on very rudimentary level, companies that can create building blocks from those technologies, and end users that can use these technologies, these building blocks, to create smart missions in the end.
Okay, fantastic. Yeah, that's really interesting. We're used to dealing with certain standards and levels of performance in space, and you sometimes when you take a step back and think, for any terrestrial application, if you were only getting 20% of useful data, that just wouldn't be acceptable. So that's really illuminating why solutions like onboard data processing are required. In terms of the technologies and systems that you've just mentioned, what sort of new capabilities can these solutions bring for satellite missions?
The AI on board a satellite can not only help the payload and the mission objective, but also aid the satellite operation itself. And again, in the old approach, we were limited by the cost of communication, expensive communication, and satellite was very dependent on ground station. And a lot of images that we send, as I said, are cloudy or shaken, and they're really invaluable. And the numbers are quite shocking, how many of them are invaluable. So the most rudimentary task that you can perform with onboard data processing and AI is to discard data that is invaluable. Transfer a lot of data to Earth, but you can at least discard what is invaluable by making satellite be aware of what it has gathered. And you can also mask out parts of images that are cloudy, use AI to detect clouds on images, mask them out. And this really helps image compression algorithms. So even without actually doing anything smart on satellite, the most rudimentary thing you can do is to help the compression and transmission. At the most basic level, you don't have to change too much, but you can discard what is invaluable. And this is already a huge improvement, but this is just the beginning, because cloud detection can be treated as a pre-processing step for further image analysis. So I believe the cornerstone, the starting point is cloud detection and making satellite aware of what is gathered. But again, this is just the beginning. And for example, in the smart mission ecosystem, as I said, we have a lot of very convenient tools and software to aid the mission itself. And for example, offer a modular software system called Oryx. And it comes with a scripting engine, which enables you to change the mode of operation of satellite on the fly. So you can rewrite what your satellite should do without tackling the low level software. And you don't have to think about the bridge between hardware and software. With the modular scripting engine and Oryx, you can just write what your satellite should do in a very user-friendly scripting language called Lua, and just update the script. And the scripting engine will understand it and adjust the satellite to your needs. So this is, again, a different side of the revolution that enables us to perform these onboard data processing tasks. But when it comes strictly to them, to onboard data processing and AI, we again have to differentiate smart satellite and smart payload. And the first one is to aid the satellite operation itself. And we can do this by using AI to analyze telemetry data, because satellites have onboard sensors that monitor different parameters. And this is what smart satellite is about itself. What it can do, smart satellite can help to analyze the logs, the telemetry, and provide onboard maintenance, keep your satellite in good health and avoid failures. And on the other hand, we have this second branch of smart payload, which offers AI capabilities regarding the mission objective, image analysis on board of satellite for Earth observation tasks and image processing in general.
Two sides of the coin there, but really interesting that it's the same solutions enabling both. You've mentioned a number of these already, but I wondered if you could give some further specific examples of how algorithms and processing tools can support different kinds of mission.
Yeah, there are tons of exciting ideas and specific examples that we can provide. Let's get back to the maintenance and telemetry analysis tasks, because they are really interesting. And anomalies and failures can be really straightforward. Let's take an example of out-of-band failure. So to detect such a failure, like for example, too low voltage power supply failure, you can just threshold the telemetry data. This is a really straightforward thing to do. However, there are many failure scenarios that are harder to detect, called contextual anomalies. And this kind of anomaly can only be detected by AI nowadays. And what contextual anomalies are? They occur when every single signal on board of satellite is incorrect bounds, incorrect range, and it seems fine. However, when you look at them and compare them, how they relate to each other, it may come that even though each one of them is perfectly fine, they are in combination in a situation where they should not be during normal operation. And this is really important. And detecting such a failure is only possible with AI, but if it is possible on board of a satellite with AI, you can really take some steps. You can try to mitigate this problem automatically. And this is a huge difference, because if you were to try to mitigate failures with the traditional approach, you would have to gather the logs and then wait for your satellite to fly over a ground station, transmit these logs, analyze them in the ground station. And after you detect a failure, it may be too late to do anything about it. You may have missed the moment when you could have taken the action. And this is why you want to be able to detect the failure on board of satellite and have some failure handling scenarios. In case something happens, you can detect them with AI and start rescuing satellite in orbit without actually having to wait for the communication session to begin. This is really important, and it makes a huge difference, because actually I have another example of quite shocking number, because from year 2000 to 2015, little over 40% of small satellite missions experience at least partial failure. And this number is provided by NASA, so it's insane number. And smart maintenance and fault handling are crucial key points to mitigate this problem and really help satellites to operate in a more correct way. And this was more about the smart satellite, but now let's move on to the smart payload, because this is where maybe the most interesting and most spectacular things may come. So we work at KP Labs on several machine learning algorithms for Earth observation. And I have already mentioned the most basic task of cloud detection, because it can help to utilize data transmission better. But the possibilities are far beyond that. And we work, for example, on smart farming algorithms. And with AI, it is possible to estimate soil parameters from a satellite image. And this is a really interesting idea, and something that is hard to wrap your mind around when you think about it, because you can estimate, for example, how much potassium ground contains just from a satellite image.
Just from the image of the surface, yeah.
Yes, but actually it is something more than image of surface, because you capture image of surface, but we work with very specific images. They are generally called hyperspectral images. And even though they capture what the ground looks like on the most basic level, they cover the light spectrum beyond visible wavelengths. And they are very feature rich, and they capture data in infrared, ultraviolet, or radio frequencies. And this is why you can estimate, you can infer such complex parameters, soil quality, just from a satellite image, which is really interesting and was never heard of previously until AI and hyperspectral data came into play. So you can really think of those images as scientific scans or using scientific apparatus than normal images that we are comfortable with. They are much more than just RGB images. And alongside our domestic work on soil analysis, we organize an open for all challenge in this topic of soil quality assessment. And we provide data and metrics for competition that we have prepared. And because hyperspectral data is so feature rich, we advertise the competition with a see beyond visible slogan, because hyperspectral data, it creates images, but the images contain things beyond what you can see with your own eyes, which is a really insane idea. And this initiative, this competition of soil analysis, is supported by European Space Agency. So I definitely encourage everyone listening to this podcast to try it out. You can join the competitions, and there are some nice prizes for the winners. So definitely check it out. And going back to the benefits of using AI versus the traditional approach, again, we are doing a lot of these comparisons. You may ask, what is the difference between analyzing soil with AI, with satellite, versus how it used to be done before, how it is done actually now? So we have experienced this firsthand when we were gathering data for our competition. And we were cooperating with people that work daily with soil analysis. And how they do this now is that there is a guy who has to rent an ATV and drive around crop fields and gather some boxes, some probes of ground, and pack them in a larger box, send them all to a laboratory. Laboratory has to run some analyses with a scientific apparatus, and it's something that you have to really organize people, equipment, vehicles, a laboratory. And it's a process that can take weeks or even months to cover a large area of crop fields. And with satellites, we are close to a point when you can just order a analysis of soil with satellite, click a few buttons, and have results delivered in hours or perhaps minutes one day. So it's a really, again, interesting idea, and there is a huge difference. Numbers are really on the side of smart satellites. And we are not only working on soil analysis, but there's another interesting and novel idea regarding super resolution tasks. And super resolution is a technique for enhancing quality of images, enlarging them with extra details created by AI. And you may have used it if you have Photoshop installed, because I believe nowadays, if you stretch out image and you enlarge it, you may use an AI algorithm built in Photoshop to add some details and sharpen the image, enhance the quality. And this is how this technology has been mainly used for aesthetic purposes and for manual analysis. However, now together with European Space Agency, we are running a project for using super resolution as a data fusion step, as a pre-processing step to aid the further data processing. So for example, let's imagine that you have a air observation task like monitoring fire spread, for example, or tracking vessels. And with super resolution, before you apply AI to the final task, this, for example, vessel tracking, you can use super resolution to first enhance the image, make it sharper, so it's easier to detect the vessels by the final algorithm, because it gets better quality images at the input. And this is a very novel idea of super resolution in task-based environments. And this is what we are working on. And beyond what we work on at KP Labs, there are many more use cases that may come into play. And there are people around the world preparing different AI solutions for tasks like, again, vessel tracking, anomaly detection, natural disaster monitoring. And some time ago, I came across a really interesting model to predict possibility of car accidents at specific crossroads from satellite photos. Yeah, it is really cool, and it's connected to safety, so really important topic. And AI was able to take a photo of some network of roads and estimate which crossroads were most prone to accidents and crashes. So it's a great tool for city planners and stuff like that, and possibilities are really endless. And there are many benefits in general to using onboard data processing and AI. And one thing to note is that in general, running AI on satellite is an asset and not a must. So we can deploy any way we want. We are very flexible. Nevertheless, there are some use cases that are uniquely available thanks to onboard processing. Like the best example is this online risk management with telemetry analysis and failure prevention. However, there are some new exciting ideas that are close to being implemented, like in-orbit rendezvous operations, where a swarm of devices, of satellites or space vessels with a high degree of independence can cooperate together. And this really requires a high level of autonomy to run successful, to cooperate actions between different vessels and satellites in orbit.
Yeah, that's amazing. There's some really interesting use cases there. There's quite a few things that stood out to me. The online telemetry tracking and the failure prevention is fascinating because presumably the larger the satellite, the smarter the satellite, the smarter the payloads on the satellite, the more important such capabilities become. As the satellites are more expensive and heavier, you want their ability to be able to track the telemetry and prevent what failures you can. So that's interesting. And yeah, we talk a lot about at satsearch because we're viewing both sides of the marketplace. You do a lot of comparisons and a lot of discussion of competition in the industry and what are alternative solutions to things. But you never think of it as when the sort of applications you're talking about. You never think of it as satellite versus the guy in the truck driving around collecting soil samples. But to the end user, that's the comparison they have to make when they're trying to decide which is the best solution to finding out the soil quality. So really interesting stuff. Thank you very much for sharing a lot of that. So we talked a lot about the processing capabilities and the results that such onboard processing and AI can bring you. What sort of hardware is required in order to use it in the first place?
Modern AI in general is a very demanding software to run in all conditions. I would say perhaps it is one of the most demanding in terms of performance software kinds to run. So when we talk about running AI inference in domestic conditions, graphic cards are often used as accelerators, and they may be built into your computer, and they are used in data center. They are great, they perform great, and they are a standard. However, what works well on the surface is not that suitable for space missions. And when it comes down to satellites, the trade-offs between power consumption and performance are really crucial for efficiency management, because there is always a risk of your satellite running out of juice. And this is a really important risk and something that you have to be aware of. So first thing is that the trade-off between power and saving energy is really important. It's more important than in normal conditions. And also the hardware flexibility factor has a different context in space, because you can easily swap GPU models in your computer, and you can just take out parts of your computer and install new ones. However, this can't be done in orbit. Unfortunately, you can just take out pieces of your satellite as it operates. And for this reason, at KP Labs, our accelerators are mainly FPGA based, and this enables us a new flexibility. And FPGAs are very specific devices because normal processors can be programmed with different software. Our computers can perform different tasks because they run different pieces of software. And FPGAs are like that, but they are even more programmable, because not only software is programmable, but also hardware can be resynthesized on the fly. You can describe different hardware architectures, and FPGAs are able to readjust on the fly on the hardware level. And this means that different trade-offs can be balanced during the mission. For example, you can prioritize single core performance over multi-threading or vice versa in orbit, and also really prioritize energy saving when it is crucial and you are close to running out of juice again. So flexibility and power consumption and performance are key factors in modern AI hardware for space. And when it comes down to KP Labs and what we offer, we have 3 different AI accelerators for satellites: Antelope, Leopard, and Lion. And let's briefly walk through them. So Antelope is the most lightweight unit, and it is designated to add the smart satellite. So we are talking about this maintenance tasks, anomaly detection, failure prevention. Antelope is an AI accelerator that is designed to run algorithms to perform these tasks, to help the satellite operation itself. However, Leopard, which is a medium-sized all-rounder, is more focused on smart satellite. So it is designed for image processing, for Earth observation tasks, like cloud detection, segmentation, soil analysis. This is the difference between smart satellite and smart payload. And last but not least is Lion, which is the bigger brother of Leopard. It is the beefiest unit out of them, and it is designated for the most demanding space missions. Whereas Antelope and Leopard are designed for CubeSat missions, Lion will work with standard DPX space missions for satellites over 50 kilograms. So it is definitely for the biggest contenders. I have told you about all those algorithms and hardware pieces and what we can do with them, but we do work hard not only on prototyping them, but we work hard also on turning these possibilities into real life advantages and space missions that are implemented in real life. And this is why we launched our in-house satellite mission called Intuition One, which will carry Leopard on board and perform smart farming and soil analysis tasks. And furthermore, we have invested in making sure that our development environment is really user-friendly. And we put a lot of emphasis of the telemetry and safety and robustness with Antelope, and the development environment and simulation environments to make sure that you develop your satellite in a very convenient and very robust way. And this is why we support a second mission called PWSat-3. It is a mission run by students and scholars from Warsaw University of Technology in Poland, and we provide them with our solutions, and we are really eager to cooperate with them and offer our support. PWSat will carry Antelope and test the telemetry analysis algorithms, and we are really looking forward to cooperating with students and scholars and trying out how user-friendly and how efficient our development tool chains are and our solutions and how end user can benefit from them. And once again, I would like to highlight the flexibility and the hardware of the flexibility of our hardware and software, because Leopard is based on FPGAs and can be reprogrammed in orbit to support different hardware accelerator architectures. And Oryx, our modular software, enables you to reprogram satellite operations. And this leads to very reusable, very adjustable satellites. It means that a single satellite can support different goals and missions as the time progresses. And because of these wide capabilities and variety of tasks at hand, we call Intuition One our mission, with Leopard on board, a flying laboratory that can perform diverse experiments and really try out new possibilities, different possibilities during the same mission.
Very interesting to understand what some of the technical considerations are. And obviously, engineers, you've mentioned some of the things that they would need to consider when trying to implement their own solutions using onboard data processing and AI. You've mentioned the importance of considering power efficiency, and also in the first instance, thinking about how you're using the tools, whether it's to enable that smart satellite concept and analyze your own telemetry data, or whether it's a smart payload situation, or both, of course. So I wondered what other sort of technical considerations that an engineer would need to factor, and then the trade-offs that they may need to think about when integrating the hardware and the software into the satellite and deploying it on orbit.
This is a really important topic because the engineering is what drives satellites. And when it comes to satellite drivers and software development, it used to be a pretty daunting task in the past. And a lot of things had to be written from scratch. And often you had to use a very obscure hardware and program it from the very beginning. However, a huge progress has been made with the emerging new space paradigm. And nowadays, with technologies like our space smart mission ecosystem, creating satellite software can be a much more developer-friendly, user-friendly task. And our development process and what we offer in form of building blocks encourage good programming practices with modern coding standards. And this means that we build highly testable code that works with CI environments. And this is really important to software developments because nowadays programming tools, CI/CD, DevOps becomes more and more indisposable. So every software developer will really appreciate this process of creating highly testable code that works well with existing software tools. And we really put emphasis on unit and end-to-end testing. This not only means that our satellite software is robust and you are confident in how it works, but you can also create your software on top of it with great convenience and using the software tools that we provide. So not only the building blocks are really great and created in a very cautious way with good coding practices, but you can follow the way we create software, a development toolkit provided a way of creating software that is really user-friendly and really convenient. And on the other hand, AI in space is a relatively new thing and it's still maturing. And at KP Labs, we work really hard on pushing the frontiers of AI on board satellites and raising technological readiness levels of new solutions. And as mentioned, the hardware to run AI in orbit is pretty novel and it's very different from standard GPUs. And it comes with a ton of benefits. And I have praised the flexibility of our hardware and FPGAs, but it comes with a cost of having a lot of parameters to fine tune and tweak. And at first glance, it is really hard to know how to get the optimal configuration for the mission at hand because you have so many possibilities. And this is why we have developed our custom benchmarking process for robust AI deployment on board satellites. Because there are tons of existing benchmarks and the majority of them is great and they work fine for choosing your hardware platform, for choosing your hardware vendor, hardware family. They are great for this purpose. However, after you have chosen what you want to use and you have it delivered, these kinds of benchmark, they tell you really nothing about how to utilize best what you have chosen, how to fine tune it, how to tweak it. And this is how our benchmarking process differs and when it comes into play. After you have bought your solution, you can use our benchmarking process to fine tune it. And we have created this process while evaluating our hardware, our Leopard AI accelerator. And you can think of this benchmarking process as painting the landscape of what the hardware is capable of under different circumstances. For example, we created our benchmarking process with different sized real-world neural networks with different use cases, operational modes, and configurations. And in the mathematical terms, you can think of this benchmarking process as creating multi-dimensional matrix or tensor of various scenarios, various configurations, various parameters. And we have the results quantified and measured in relation to power consumption. So we know how to turn the knobs in a way that really works as intended. So the trade-offs regarding our hardware are balanced in a very conscious way. And this not only helps us to scale hardware in current solutions regarding what we work on now, but it provides us with confidence and knowledge about future deployments. And we can easily predict what we are capable of and what can be easily implemented and what is the best path to take if we were to invent something new and deploy something new, because we have such a broad understanding of how our hardware scales. And this benchmarking process was applied to Leopard. However, this workflow of benchmarking we have developed is available public, so we encourage all AI in space practitioners to check it out and follow our steps to perform benchmarks in a similar spirit and evaluate their hardware pieces. So the general knowledge of this field, the know-how, it grows with continuing experiments, and we are more and more mature with the hardware platforms that are in our possession.
Thank you. We'll link to that in the show notes as well, the benchmarking process, or I'll provide some more info. And you mentioned that is obviously a solution that enables you to determine or prepare for future deployments. And I wondered if you could zoom out a little bit and think about future deployments of AI and onboard processing in general in the field in years to come, not just the next sort of mission schedule. What do you think, what capabilities and opportunities you think satellite data end users and mission designers are likely to have access to in the years to come?
Okay, so this is a really interesting question because it is just a starting point. We are just at the beginning of this path of truly autonomous space systems. And in recent years, we will experience raising the technological readiness level of the solutions that I have described. So easy to use, feature-rich satellites development systems are nearly at hand. And the accessibility of onboard data processing and AI in space really will enable us to see more complex solutions being built. And we will see things like satellite swarms and fully automated satellites to come soon. And next to this, we can expect a marriage between cloud computing services and satellite technologies. And it started happening right now because Amazon Web Services, which is the most popular provider of cloud services, already provides a satellite ground station service This is a very basic thing, but we're, again, just at the starting point. But we really can expect a moment when satellite missions will be part of a bigger autonomous system of swarms or of connections between different computers, semi-autonomous autonomous systems, systems of automatic decision making. This is really interesting, and AI plays a huge role in automating Earth observation processes in general. And onboard data processing will definitely decrease latency and streamline satellite operations. And in years to come, businesses will be able to order satellite observation analysis on demand with AI insight delivered on the spot. And maybe like even common people and like every Joe will be able to order a satellite observation with a few clicks and have some interesting insight delivered by AI. So in the far future, AI and onboard data processing will hopefully help to launch even more exciting and sci-fi-like missions like smart space vessels and robots. And there are some interesting ideas regarding satellite mining and really interesting things may to come if you look in a very broad perspective. But also really interesting and novel things are really close and really at hand to come in years to come.
Quite a vision of the future, and I think there's so many things that so many people in the industry and followers of the space industry would like to see happen, and maybe in some cases expected to see happen by 2022. And obviously the sort of technologies you're talking about can form a core part of enabling that. So that's been brilliant. Thank you very much. The insights you've shared with us today, I think, will be really interesting to the community. And on behalf of satsearch and all of our listeners on the Space Industry Podcast, I'd like to say thank you very much for spending time with us and sharing that information.
Thank you very much. It was a great opportunity to talk with you.
Thank you. And to all the listeners out there, you can find out more about KP Labs, the smart mission ecosystem, and all of the tools and technologies that have been discussed today on the satsearch platform. We'll link to the details of that, and you're free to use the request system to get in touch with the company and learn more. And we'll also share some of the resources that were mentioned. And would encourage you, if you have any interest in this area, if you have professional applications of the tools and technologies discussed, to get in touch. And finally, I'd just like to say thank you all for listening and spending time with us on the Space Industry Podcast. And we'll be back soon. Thank you for listening to this episode of The Space Industry by satsearch. I hope you enjoyed today's story about one of the companies taking us into orbit. We'll be back soon with more in-depth, behind-the-scenes insights from private space businesses. In the meantime, you can go to satsearch.com for more information on the space industry today, or find us on social media if you have any questions or comments. To stay up to date, please subscribe to our weekly newsletter, and you can also get each podcast on demand on iTunes, Spotify, the Google Play Store, or whichever podcast service you typically use.